This tiny blue token is about to generate one word, but before it can, a laptop with 25 gigabytes of memory may have to move roughly 11 gigabytes of model weights for one token. The model is GLM 5.2, a 744 billion parameter class mixture of experts. The file on this drive is about 372 gigabytes. The machine has no GPU, and yes, the token can still make it through. That sounds like the whole model somehow fits in 25 gigabytes. It does not. The real trick is more interesting. Colibri stops treating RAM as a box the model must fit inside. It treats VRAM, RAM, and NVMe as one managed memory hierarchy, then moves only the weights the router proves this token needs. Follow this token through the system, and the claim becomes precise. You will see what stays in memory, what streams from disk, why the slowest machine produces only about one token every 10 to 20 seconds, and exactly when this setup is worth using. First, separate model size from active work. GLM 5.2 is sparse. Each mixture of experts layer contains 256 routed experts. For the current token, the router selects 8. A shared expert and the dense attention path also run, but most routed experts remain inactive. Across the network, roughly 40 billion parameters participate in one token instead of the entire model. Sparse does not mean small. All the weights still have to live somewhere. It means the computation touches a narrow path through a much larger archive. Watch the token enter layer 1. The router scores the experts. 8 IDs light up. At the next layer, it may choose a different 8. Colibri records those choices, predicts useful work one layer ahead, and stages the selected expert matrices from the fastest tier that already contains them. This is the first big correction to the usual explanation. The current Colibri path is not simply download a 2-bit GGUF and run it from disk. Unsloth does publish 2-bit GLM 5.2 files around 239 gigabytes. But Colibri version 1.1 uses its own quality-preserving int4 container, about 372 gigabytes, with an int8 speculative head. Mixing those two setups makes the tutorial smaller on paper and wrong in practice. Now open the laptop. The memory subway has 3 stations. At the top is compute. This is where attention, routing, and matrix multiplication happen. In the middle is RAM. About 17 billion dense parameters stay resident there. At int4, that core occupies roughly 9.9 gigabytes. It includes the embeddings, attention path, and shared experts needed again and again. Any remaining memory can hold a hot expert cache. At the bottom is NVMe. Colibri describes 19,456 routed experts across the model and its prediction head. Each expert is roughly 19 megabytes in the current container. Together they occupy about 370 gigabytes, parked on disk until selected. Our token reaches a layer. 8 experts are requested. If one is already resident, the root flashes green, and compute starts immediately. If it is cold, Colibri reads its adjacent matrices in one operation. A bounded I/O pool overlaps missing reads with resident computation. A look-ahead thread prefetches the next layer because routing has enough structure to make prediction useful. After the turn, a learning cache remembers which experts this workload uses most. Nothing about that placement is supposed to change the answer. The same router decisions and the same weight precision apply, whether an expert arrives from VRAM, RAM, or disk. Placement changes speed, not semantics. That is the engineering idea worth remembering. Parameters become staged data, not mandatory resident state. There are 2 more pieces that keep the subway from wasting trips. The key value cache is compressed, so a long conversation does not expand into the usual attention memory bill. And GLM 5.2 includes a prediction head that can draft multiple tokens for the main model to verify together. Colibri reports roughly 2.2 to 2.8 accepted tokens per forward pass when speculation pays. But the project disables the fantasy math. A draft only helps when its extra work costs less than the verified tokens it saves. Cache temperature and workload decide that, so the correct default is to measure. Now prove the setup with the current release. Start with Colibri version 1.1. You can use a pre-built release or clone the repository and run its setup script. The engine itself is pure C. Python handles the launcher, conversion, and optional API gateway. Next, get the current GLM 5.2 Colibri int4 container with the int8 prediction heads. Budget roughly 372 gigabytes for the model, plus working space. Put it on a local NVMe drive. A network share or slow external disk defeats the point. Before starting a chat, ask the engine for a placement plan. Set the model path, then run Colibri plan. This does not generate anything. It shows where the dense core, expert archive, caches, and optional GPU tier will live on this machine. Then run Colibri Doctor. That is the safe readiness check. It catches missing files and incompatible placement before you wait through a first token. Finally, run Colibri Chat. On the 25 GB floor, the status should show roughly 10 GB resident and the routed archive on disk. The token enters the same subway we just built: route, place, overlap, compute, learn. The first token deserves its own warning. It can take much longer than steady decode because the engine must load metadata, warm caches, and process the prompt before generation begins. A million token context window on the model card is not a promise that a 25 GB laptop can fill that context quickly. Context capacity, time to first token, and decode speed are different constraints. And now the bill arrives. Colibri estimates that about 11 GB of routed weights change from token to token. On a cold path, storage must serve a large share of that data. If the useful read rate is 5 GB per second, 11 divided by 5 is already more than 2 seconds of transfer before the rest of the work. Real access is fragmented across layers, compute still takes time, cache hits vary, and operating system behavior matters. That is why a clean bandwidth division does not equal final token speed. The project reports about 0.05 to 0.1 token per second cold on the original 25 GB development box, 1 token every 10 to 20 seconds. A paragraph can take many minutes. This is not an interactive coding assistant, it is an experimental overnight worker, a privacy-sensitive batch tool, and a way to inspect a frontier-scale open model on hardware that should not be able to hold it. If a smaller 32 billion parameter model answers your task well, that smaller model will usually be the better local product. The more useful story is the dial between disk and residency. With a 128 GB CPU-only desktop, community measurements in the project reach roughly 1.8 tokens per second warm. A single laptop class 5070 Ti system is reported near 1.07 tokens per second through the GPU resident pipeline. 65090s with full residency reach roughly 5.8 to 6.8 tokens per second. Those numbers are not a universal benchmark. They show the same rule on different machines. Every expert already resident in a faster tier is an expert the token does not have to fetch from disk. 2 SSDs can help too. Colibri can keep a byte-identical model mirror on a second drive and distribute expert reads by measured bandwidth. A 9 GB per second drive plus a 3 GB per second drive provides about 1/3 more aggregate read bandwidth than the fast drive alone. Again, measure your hardware. Direct I/O, cache temperature, drive controller, and the prompt can all move the result. So here is the decision rule. Use the 25 GB configuration when the goal is exploration, offline jobs, or proving that the architecture works. Use more RAM, a GPU expert tier, or multiple drives when you need a result before coffee gets cold. Use a smaller model when latency and repeated daily use matter more than running this exact frontier scale checkpoint. The breakthrough is not that 372 GB magically fit in 25. It is that they no longer have to. The dense core stays. The router chooses. The hierarchy stages. The token moves. Once you see models as traffic across memory tiers, can this machine run it? Stops being a yes or no question. The better question is, which weights must be resident, which can wait, and how much latency are you willing to buy back? That is the real mechanism behind GLM 5.2 on 25 GB of RAM.